This is lecture number 2 in signal processing. Last time we concluded our lecture by learning about the basic operations, and I pointed out that while you are performing basic operations, so all the basic operations are on sample by sample basis. So if you are asked to add two signals, so you need to add the values at corresponding indices together. So value here which is 0, so this plus this, this plus this, this plus this, and similarly. So if something is not defined, means it is 0, it is 0 everywhere else. We also learned about the few basic signals. We said this is a basic signal which is 1 add 0, and it is called delta of n. And we also learned about the ideal delay, that if I write delta of n minus 1, it means the same impulse at 1. If I write one, actually it is different from the direct delta function which we encounter in analog signal processing. Right? It is not that delta. It is very well defined delta. That delta is very confusing. That in signal and system you must have learned about the direct delta, which is a function of t, which is time, and you say it is a delta where this delta is approaching 0 and its height is 1 over delta, its width is delta where delta approaches 0, and its area under the curve is 1. It's very theoretical signal which cannot be produced in real life. On the other hand, a discrete time delta is something very real. It is just, if you writing it in an array, you write 1 and 0, 0, 0, 0. So this is a delta. Okay? 1 at 0 index and then 0 otherwise is a delta. So, and its amplitude is 1. If I say its amplitude is 3, let's say if I ask you to write 3 delta of n. So a 3 delta of n is an impulse at 0 with magnitude 3. Right? So this is 3 delta of n. Similarly, if I ask you what is 2 delta of n minus 2, so it will be so this is 3 delta of n. So what is 2 delta of n minus 2? It is a signal at 2 with magnitude 2. What is minus 3 delta of n plus 3? This is at minus 3 and magnitude is minus 3. Okay. If I add all these together, and remember the addition is on sample by sample basis, so once you add, you get something which is minus 3. It is minus 3 at 3, then minus 2 0, minus 1 0, 0 it is 3, 1 it is 0, and 2 it is 2. So this is the same. Okay. So this is how you can write a signal primarily, and that's what we intend to learn in this part of the course, that how to represent a generic discrete time signal which has just values, a sequence, and this is how you can really write it in a mathematical form. So mathematical form is x of n is minus 3 delta of n plus 3 delta of n and plus 2 delta of. So this is how you write a discrete time signal. So a discrete time signal can be written as a summation of these impulses, and we call this, that to generalize this, I can say that I know that at every index there is a value. So value of the signal at index -1 is represented by x minus 1. Value of the signal at 0 is represented by x of 0. Value of the signal at 1 is represented by x of 1, and this is x of 2, and this one is x of 3. So to generalize signal representation, I know that a signal is basically a summation of all these signals. So weighted shifted impulses. So you write x of -1 delta of n plus 1, because this is the impulse at -1. Then x of 0 delta of n plus x of 1 delta of n minus 1 plus x of 2 delta of n minus 2 plus, so you can go on any side. So you can go to the positive side or the negative sides. Just keep writing it like this. So it means that in general you can write, there is a way to put a sequence in mathematical form, and this is the mathematical form. And to put it in a closed form expression, you write it as a summation. K goes from minus infinity to infinity, x of k delta of n minus k. So this is the closed form expression for representing a discrete time signal. So it is a summation of weighted shifted impulses. Summation of weighted shifted impulses, and that's how we write a discrete time signal. Okay? So this really brings us to the end of a signal representation. So signal representation is can be conveniently written as a signal is basically an impulses, scaled impulses. So if you can represent each impulse, we know how to represent each impulse, and if you add them together you get the signal. So a signal is a summation of scaled shifted or weighted shifted impulses, and that's how we define a signal as sum of weighted shifted impulses. So a signal is basically this impulse and this impulse and this impulse. Once you add them together, mathematically addition operation will give you the signal. So this brings us to systems. What is a system? Okay. So, and primarily we'll first learn about analyzing a system in time domain. System is any operation which you perform on a signalless system, as I mentioned earlier, that if you even write 2x of n, so this is a system. So you are producing an output sample by multiplying your input signal, all samples of input signal, by 2. So any processing happened to your signal is a system. Now interestingly, there is some processing which you intend to do, so you are actually doing it in your algorithm, but then there is some processing which is happening which is not in your control, which is happening by the nature. So nature is applying a system on many signals. Example is, I'll keep giving you this example, that your mobile phone and your base station. Okay, so your mobile phone is transmitting, let's say you transmit one impulse. So this impulse will go and hit the antenna on the base station. So this is a system. Okay? So what is a system? System is this entire atmosphere, or we call this channel in signal processing. This channel is a system. Now this is an impulse which was transmitted at the transmitter at 0 time, or let's say it just reaches at the base station getting some attenuation. So once it hits this antenna, it is attenuated by 0.3. Okay? So what the system is doing, it is acting as an attenuator. Let's also assume that there is the same impulse, because being transmitted, it hits the ground, okay, and reaches at the antenna the same impulse. You only transmit impulse and then you don't send, for example. So it reaches at the antenna attenuated and delayed. Sorry, this is not delayed. Let's say this is delayed by one sample delayed. Okay. Then let's assume there is another, the same impulse getting through this building and reaching here at by attenuated by this and delayed by, let's say, 2 time units or 3 time units. Okay. So now this is a system which is corrupting, because this is not a desired processing, it's not a desired system, this is an undesired system, but you need to counter this system. So the system, what the system is doing, a signal which is being transmitted is coming through so many paths. It's called these multi-paths. So it is coming through multi-paths to your antenna.
All of this is considered one system?
One. This is one system, Ji. This whole thing is a system. From the transmitter to the receiver is a system. Okay? But this is an unknown system, you don't know. But to counter the system, because you don't want this, you want whatever is being transmitted, you want to have the same. Right? So this is a very challenging problem in digital communication. It is called multi-path problem. Okay? This is multi-path and multi-path fading problem. That not only you have multi-paths, but the paths are also fading your signal. So once you transmit, you're not receiving what you transmit. Now at the receiver, using signal processing techniques, you need to pass it through another system, that is your desired system. Okay? So you need, whatever you receive, you need to pass it now through your system, and you want, once this system should counter this system, and what you get at the output is delta of n. And remember, Ji, Ji, the question is this transmitter and is also a system? Yes, it is a system. It's a discrete time system. Every component in this system is a system. For example, antenna is a system. Okay? Amplifier is a system. So every component in this is a system. It's a cascade of so many systems. It's nothing but system and system and system and system. You transmit, you get in air is a system. Okay? You get down to this antenna, this is a system. So this whole thing is a system, and so you then, something which you design is also a system, but this is your design, and this design is to cater for what is happening to your signal, a multi-path fading. So you try to take away multi-path fading effects. So but what really I want to highlight here is that once we say system means any transformation, whether you are doing it or anybody is doing it. If your signal gets transformed, it means the transformation has happened due to a system. Okay, so we may call this a transformation, that input signal goes through a transformation, you should get an output signal. So this, where T is an operator that maps an input sequence X of n into an output sequence. There could be different types of systems, right? All kinds of, anything you do to a signal yourself is a system. For example, I ask you to, whatever you get, okay, you take square of that. Okay, this is a system. Because you are doing some processing, I say it is 1, it is minus 1. I say, okay, what you do is, whatever sample you have, take its square. So you say it is a system which is taking square. So it is 1 and minus 1 square is also 1. So this is the output. Okay, this is a system. I say no, what you do is add this sample in the previous sample. So whatever you get, add it in the previous sample. This is also a system. So a system where you are adding a value to a previous sample. So you, at index 0 you get 1, at index minus 1 what do you have? A 0. So 1 plus 0 is 1. So you say 1. Now you are at 1. 1 minus 1 is 0, so you put 0. Then here you have a 0. 0 minus 1 is minus 1, so you put minus 1. Now 0 plus 0, 0, 0 plus 0, 0. So you need not to go forward because you know you will be getting all zeros. And similarly, if you go back, you will be getting all zeros. So this is also a system. Right? I say, okay, you can add, you can subtract. I ask you, no, add 3 previous samples. Take the current sample, add 3 previous samples. This is a system. Okay? So anything you are doing to your signal is a system. Okay? Sometimes you are performing linear operations. So we'll learn about what is linearity. So linear is you learn in mathematics that something is a linear operation or non-linear operation. Right? If you apply linear operation to your signal, it is called a linear system. If you apply non-linear operation on your system, it is called non-linear operation. For example, addition, subtraction, these all are linear. Multiplication, these are linear operations. If you are performing these operations, this is a linear system. Right? If you are performing this operation, which squaring is a non-linear operation. Right? So let's now exactly define what is meant by linear and non-linear operation, and why it is important and critical to know this, that whether you want to apply linear operations or non-linear operations. So we are really interested in knowing linear system. A linear system is a system where you apply linear operations. So it obeys, we say, linearity means the principle of superposition. What is principle of superposition? Superposition says that if the input of a system contains the sum of multiple signals, like this is a system, you apply one signal, you get an output. Okay? So we can really describe it like this. This is your system, and you apply one input. Let me call this x1 of n. You get an output, y1 of n. Then you apply some other input to the same system, and you are performing the same operation. So you take another signal, you apply the same operation on this signal, you get another output. Now you add these two signals together. Okay? So there are two parts to linearity. One, this is called additivity, that you add them together, plus x2 of n. So what you get at the output is, if you get this, it obeys the first principle of linearity, that additivity is satisfied. Any operation which obeys this means that it is linear, but still you need to check another property, and that is scaling. That if you scale this by, let's say, alpha, then what you get at the output is the same output what you got previously, and the output is only scaled by alpha. Similarly, if you scale this by beta, you get nothing but an output which is scaled by beta, same output. Okay? So if you have an alpha x1 of n plus beta x2 of n, and you get alpha y1 of n plus alpha y2 of n, it means your operation which you're performing is linear. Example is an integration operation. You must have learned the properties of integration. You say, okay, integrate alpha x1t plus beta x2t dt. And you say, okay, this integration is really, you take alpha out, you say x1 of t dt plus beta out x2 of t dt. So integration is a linear operation, because if you scale your input, you simply scale your output. If you are adding to inputs, you individually apply the same operator on individual inputs and add the answers together, you get the same answer. Differentiation is a linear operation, but our interest is in discrete time operations or operators, that what type of operators in discrete domain can you apply which obeys the principle of linearity. So the squaring is not a linear operation. Let's do an example to demonstrate this. So squaring, I'm saying squaring is not a linear operation. So let's say this system squares. So you have a signal which is 1 and minus 1, and you have another signal which is minus 1 and 1. Okay? So this signal, once you pass it through a squarer, will give you what? 1 and 1, add 0 and 1. And this system, once you pass through this system, will give you again 1 and 1. Okay. So now to check, what you need to do is add these two signals together on sample by sample basis. What do you get? You get 0. So you must get, if you add this, what do you get? 2 2. But if you pass 0 0 to this squarer, what do you get? 0 0. So they are not matching. So if they are not matching, means if you are applying individual inputs, you get individual outputs. If you add inputs together, if you're not getting the summation of the output, means system is not linear. Right? So because this addition is giving you 2 2, and passing that to the system is giving you 0 0, so they are not matching, means the system is not a linear system. Right? Mostly our interest in signal processing, I should say 99% of the time, is dealing with only linear systems. Right? If a system is non-linear, for example, the system which I showed you, sometimes it may show some non-linearity. Let's say maybe the atmosphere is squaring your impulse or doing something odd to your impulse. Very hard to figure that out. Okay? To combat that system which has non-linear behavior. So we say if a system has a non-linear behavior, we say, okay, for a small time duration, let's assume it is linear. Like if you have this is y is equal to a parabola, x square something. I say I know this is a non-linear function, but for this much duration it is linear, then it is linear, it is linear, it is linear, it is linear, it is linear. So I can approximate it, but this becomes an adaptive system because the linearity is changing. Here it is this system, this, then this, it's a straight line, but the straight line is changing its slope. So because the straight line is changing its slope, but you can assume for a small time duration that this curve is a linear curve. You can approximate it by a straight line. Similarly, if there is a non-linear system, we make it adaptive and linear. You say, okay, this is non-linear, but I know I can say for a small time duration it is adaptive, it is linear, but then I have to keep finding the parameters. So the adaptive signal processing deals with this problem, where you are saying, okay, for small time duration it is linear, 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 but it is changing all the time. So it is changing all the time, so you have to go back and estimate. Okay, so you need to estimate the system. But our interest in this course primarily is dealing with linear systems. And so this is one property of linearity. The operation which I performed earlier, like you add a signal into a sample into previous sample, is linear. Let's check that. So this is a system where you say, let's do the same example. Here, add it in the previous sample. Okay, so add 1 plus 0 is, this gives you 1, minus 1 plus 1 is 0, minus 1 plus 0 is, so this is what you get. Now do the same with this one. So minus 1 plus 0 is minus 1, 0 and 1. This is what you get there. Okay, now you add these together, what do you get? 0 and 0, and you add this together, what do you get? 0. Right? So this is a linear system. If you are adding a sample in previous sample, it is a linear system. Right? I ask you, know what you do is add the twice of current sample in the previous sample. Twice of, add twice of current sample in previous sample. So this is a system. We'll shortly find out a mathematical description of a system. But here I am saying, okay, take twice of the current sample, then add it in the previous sample. So let's do that. So what do you get here? 2 ones are 2, 0. So you get 2, right? Twice the current in the previous sample. So twice the current is minus 2, plus 1 is? So minus 1, so minus 1. So twice the current 0, minus 1 is minus 1, and then you get 0, 0, 0, 0. Okay, so let's do the same here. Multiply the current sample. Current sample means for the index you are computing the output. Okay, current sample means if I am computing the output for index 0, 0 is my current sample. Okay, so multiply 0, index 0 with minus 2, so you get minus 2, plus 0 is minus 2, so this is minus 2. Right? Now the current sample is 1, 2 minus 1 is 1, so it is 1. So now here I am here at 0, and 0 plus 1 is 1, so I get this. Okay, now add these, what will you get? Again 0, 0. So even this is also a linear system where you are not only adding in the previous sample, you are scaling and adding. And you can just write it in any which way you want. You say multiply twice this, thrice this, add. Take the twice of current and thrice of previous and add. It will be linear. You say no, multiply the current sample with 3, the previous sample with 2, the previous to previous sample with minus 1, and then add. This will still be linear. So any operation which involves weighting of the current sample and the previous samples and adding them together to get an output is a linear operation in general. So our interest is in linear operations, and for many reasons, and we'll find out why. So linearity means that if the input of a system contains the sum of multiple signals, then the output of the system is the sum of the system responses to each separate signal. Signal output, signal output, signal output, add all of them together, you'll get the same answer. This is linearity. So this is the mathematical expression for linearity. That if you have input x1, input x2, multiply input x1 n, then output will be A, the transform of this, and B, the transform of this. So scaling and addition will not affect the output. So this is linearity. This is a system which is not linear.
You give two conditions for linearity.
The scaling
And
precisely.
Is there any system which obeys only one system?
Yes.
Or all systems
Ji.
either obeying two or one?
There could be, of course, there could be operations where a system will obey linearity, additivity, but it will not obey scaling. Okay? Means that you are performing an operation, to put it in a mathematical form. Okay? You are saying f of x is a function of x, and you say alpha of x, and this operation is f, you get this. Okay, you can take the constant out, but you cannot expand it by saying this: if f of x1 plus x2 is not f of x1 plus. So anytime if this is not true, it is not then a linear operation.
Any system either obeys both of them or obeys none of them. It doesn't obey on the single condition.
You are saying there is no such system which does this?
Is there any?
No, there must be. There must be. An example, top of my head, I don't know, but what about the square?
Square doesn't obey.
Square will not obey both, because if you add, it's different, and if you square, it is different. Yeah, square will not obey that.
Exponential doesn't obey.
Exponential sign will not obey that. But there must be some. So on top of my head, I don't know, but I let me think about it, and then I'll come back to this answer. Okay, so for sure the time invariance and linearity, you can always give examples. A time invariance is a system where if you shift the input, you get the same output shifted by the same amount, right? If you shift the input, you get the same output shifted by the same amount. Okay, this is a time invariant system. So a time invariance is a property that if you shift the input, for example, this is your input, you shift the input and bring it at 2 and 3, and you apply the same operation, the answer is, let's say you are adding and the previous value, so you get 1 and then you get 2, then you get 1. Okay, adding in the previous value. Here, so this is index 0, 1, 2. If you shift the signal to 2, 3, the same answer will be, so you'll get the same answer only shifted by 2, 3 and 4. Okay, if a system obeys this, it is a time invariant or shift invariant or time invariant system. Example of a system which is not time invariant is that if you, and this is for sure linear but not time invariant, that if you, a decimation system, okay, all you are doing is that you keep one sample and drop the other. Keep one sample, drop the other. This is a decimation system, that all you are doing is, let's say if this is your signal, okay, 0, 1, 2, 3, 4, keep this sample and drop this. Now keep this sample, drop this, keep this sample and drop this, so you get this. Now if you shift it by 1, what would you get? You get 0, 0, 0. But this is a system which is time variant. Okay, if a different time will give you different answers. So our primary interest in signal processing is to deal with linear and time invariant systems. And now there are issues, linear, and we write it like this, linear and time invariant, linear or shift invariant system. In reality, okay, we counter systems which are shift variant, which are not time variant, which rather they are not time invariant, they are time variant. Example is same mobile phone. Once you are moving, you are in this classroom, it is behaving differently because it has different paths. If you go on the road, it again has different paths. If you are just moving in your car, it has different paths. So all the time the multi paths are changing. So the system, your mobile phone system, is a very good example of time variant system, that it varies with time. Okay? So the receiver has more responsibility to always keep figuring out that what is the channel now, how the channel looks like now, how the channel looks like now. So the channel figuring out or estimating channel is a critical problem in digital communication systems. So we usually put these two together and we say our interest in signal processing is a system that is both linear and time invariant, and sometimes referred as linear and shift invariant system. Okay? जी मैं अभी बताता हूँ. So question is why it is important to deal with only linear and time invariant system. ठीक है, अब देखिए आंसर ये है इसका. Let's say you have this system which is linear and time invariant. Okay, a linear and time invariant means that, for example, if you give an input to the system, let's say input is delta of n. So this is input to this system. Let's say you get multiple reflections, and what you get here is a 0, a 0.2, and so you get 1, 0.5 and minus 0.3, for example. Okay, so this is what you get at the output. An impulse you transmit, and receiver gives you always 3 paths. Just let's make it a bit simpler than 0.2. So at the receiver, each impulse you transmit results in 3 impulses, because the signal is coming from 3 different paths. One, a direct path, gets the same without any attenuation. A path which is a reflection, giving you 0.5 fading and a delay by 1, 0.2 and delay by 2. If we assume the system is a linear time invariant system, okay, if I can assume that the system is a linear time invariant system, what will happen if instead of delta n I send 2 delta n? What will happen then? 2. So you say it's simple that you simply multiply all this by 2. What if at 1 I send minus 1? If it is linear and time invariant, if you scale the input, what do? You scale the output. If you shift the input, you shift the output. So what will you get here? So you get the same signal shifted at 1 and multiplied by 1, minus 1, minus 0.5, minus 0.2. See? Okay, now let's say at 2 it is 3 or at 2 it is 1. So what do you get here? At 2 if it is 1, so you get the same thing shifted at 2. It is 1, 0.5 and 0.2. Instead of writing it like this, I put a mathematical form to this. This is 2 delta of n, and let me call this, if I put delta of n, my output is h of n, and if it is 2, so I'm saying if I input delta of n into the system, what I get at the output is h of n. Let me give output a name, h of n. So if it is 2 delta of n, then output is 2h of n. If I put minus delta of n minus 1, so what do you get at the output? Minus of h n minus 1. Okay. So if I say h of n minus 2, delta of n minus 2, what do I get here? Now linearity tells me that if I add all these 3 inputs together, what do I get? If I add these 3 inputs together, I get here this, this and this. So 2 and minus 1 and 1. Okay. If I add this plus this plus this, and linearity tells me that if I'm adding inputs together, I should also go and add the output together to get the output, right? So you add all these together on sample by sample basis. 0, so you get 2, you get 1. Okay, so no, sorry, 0. So what do you get here? Just figure out yours. So you get something here, here, and here. The point is that we just learned that a signal, any signal, no matter what, can be broken down in terms of weighted shifted impulses, a summation of weighted, any signal. We just learned that any signal x of n can be written as a summation of weighted shifted impulses. And now I know that every impulse gives me an impulse response. A shifted impulse will give me a shifted impulse response. A weighted impulse will give me a weighted impulse response. Means if I represent an input like this, provided system is linear and time invariant, my output will be a summation of weighted shifted impulse responses for the so my output is same weight, the weight of the impulse, and instead of an impulse I need to copy the impulse response. That's it. So if somehow I can assume a system is linear and time invariant, for every impulse, if I only know this much, that what is the output of the system due to an impulse, and this is why we assume or why we only deal with linear time invariant system, that only this much knowledge, that what will be at the output if your input is a delta of n, only this much of knowledge, that delta of n will give you an h of n. If you know this, you can compute the output of the system for any input. How? Because input, you say all are impulses, weighted shifted impulses. For every weighted shifted impulse, you generate a weighted shifted impulse response, and for the signal you add all the impulses together and you add all the outputs together, you get the output. So in signal processing, all the time you are dealing with this and this. Okay, so means that if this is an identification problem, that you are trying to identify a system, I'll give you examples from latest literature that what people are trying to figure out nowadays. So if you are trying to figure out h of n, it is a system identification problem. You're trying to figure out what the system is doing to my signal. Okay, you input something, and how do you figure that out? There are ways, because you don't send impulse, you are continuously sending impulses. Okay? So from that you need to figure out that what if I only send an impulse, what will happen to my output? So this is an identification problem. If you are trying to take away the effect of an unknown system, you design your own h of n. Okay? That is a design problem. Okay? So there are different problems in signal processing. One is called identification, or sometimes we call estimation problem. And if you go to Google and search channel estimation, so you'll find so many techniques that how to figure out an h of n of an unknown channel, and something which is always changing. So what do you do then? So estimation problem is a problem where you identify h of n, and then design is a problem where you design h of n. And today I'll give you again few examples of the design problem. That you are actually designing h of n to get the desirable results. And what are desirable results? It depends. If there is a noise in the signal, you try to take out the noise. If there is a multipath effect in the signal, you try to take away the multipath. Okay? So usually in the design, you have some design goals. That okay, this is what has happened to my signal, and I want to take that out. Okay? So the design and then implementation is, this is an implementation problem. Okay? So now we have all the three problems. This is an implementation. That okay, you know h of n, then how do you actually implement a system? How do you compute output? One way is this, but this is a very tedious way, that you break your signal into impulses. For every impulse, generate an impulse response, scale the impulse response, scale, then finally add all of them together. Obviously it is not very convenient. Right? This is one way, but obviously it will work. Especially if you are writing software, it's very tedious to do this. Find out an impulse, then you have to keep so many answers, and all the time you are adding answers together. It's not very convenient, but it will for sure give you correct answer. Because this is what your understanding is really what that equation is doing. Another way is that you actually implement this equation. Okay? So implement this equation. Instead of really doing this, you say, I know this is a mathematical expression, expand it and write a program to implement this. So let's now, we know that how to actually do this. If you are given a problem, so what type of problem can you be given? A problem is, I ask you, okay, this is h of n. So a numerical question will look like this. H of n is 2 delta of n minus 3 delta of n minus 1 plus 4 delta of n minus 2. I say this is the impulse response. What is impulse response? H of n, response of a system due to an impulse. If you input an impulse, this is what you get at the output. Okay, this, and you can draw this. So it's better to always draw signals. Will give you better visualization of it. So just, this is at 0 it is 2, at 1 it is minus 3, at 2 it is 4. And always think of it as a, let's say, just the mobile and the base station. For some reason, what you transmit, okay, it gets amplified by 2, then delayed by 1, and it's a change in phase. It is minus 3 and plus 4. Right? So this is a system. If you send an impulse, this is what you get at the output. I ask you a question give me the output of this system due to an input which is equal to delta of n plus 2 delta of n minus 1. Okay, this is my question. Okay, knowing the impulse response, and I have just mentioned that knowing the impulse response means that you can compute the output of this system due to any impulse, right? So, or due to any signal. So this is the signal which is delta of n and 2 delta of. So how do you compute the answer? Simple. You say, okay, this is h of n. All I need to do is I draw this 2, minus 1 and 4 at 0, 1 and 2, 2, minus 3 and 4, and then I draw the same shifted by 1 and multiplied by 2. If I draw that and then I add on sample by sample basis, I'll get the answer. So it's very trivial to compute the answer. So multiply by 2 and shift it by 1. So multiplied by 2 will give you 4, minus 6 and 8. Okay. So now add them together to get the answer. So on sample by sample basis, you add 2 plus 0 is 2, 4 minus 3 is 1, okay, minus 6 plus 4 is minus 2, and 8 plus 0 is 8. So this is the answer. Okay. So just knowing the impulse response, you can compute output of a system due to any signal, and that is why we always try to deal with linear and time invariant systems. It helps you to only need to worry about an impulse. If you worry about an impulse, then you are done. You have solved the problem, right? Just worry about impulse, find out h of n. If you know h of n, then you are done. But the magic is in finding h of n, and h of n is nothing but numbers. H of n is nothing but numbers, right? So, and that these numbers will play the magic for you. Whatever you intend to do, these numbers, these constants, you don't just put 2, minus 3 and 4. So there is a strong rationale in coming up with these numbers. I'll give you an example which you can figure out by yourself. You say, okay, I ask you, I have a signal and I want to take out the DC value from it. I have a signal which is, let's say, I want to take DC away. DC is the level, the signal is riding on some constant value, and I want to take that away. I want you to design a system. I know a system is very simple to design. You add the current value in the previous value. Right? This will be a good system. Usually the first sample is a corrupt sample. Why? Because there is no signal here. In signal processing, the first sample is the corrupt sample, and the last samples, first few samples will be corrupt samples, and the last few samples will also be the corrupt sample, because you are not really applying, because there is nothing here. You don't know what is there at minus 1. So usually we throw the sample away. Right? But now if you apply 1, if this is 2, let's say this is 1, 2 minus 1 is 1. Then 1 minus 2 is minus 1. And now 1 minus 1 is 0, 1 minus 1 is 0, 0, 0, 0, 0. So there is this value here, and then if you do this, subtract the previous value from the current value, will take away the DC bias from your signal. This is a system. Okay? So for some systems you can just figure out the numbers, okay? And for others you may not able to do that. For example, if I ask you, in this medical equipment there is this 50 Hz signal which is riding in my medical equipment, and I want you to take the signal away. Okay? Because let's say it's an ECG machine, and ECG machine is somehow picking this 50 Hz signal, and I want, because it's just corrupting all my values, and I want you to design a system which can take away this signal. So it's not an easy question to ask or solution to make. So you need to really use techniques which we will be learning in this course, that how to take away a sinusoid from a signal, how to take away an entire band. So problem is, I say, okay, I am designing a satellite receiver, and there are several channels, and I only want to watch one, and whatever I want to watch, I want you to just get me that and throw away all the others. So this is again another, but all you need to do is design h of n. So the entire signal processing revolves around designing an h of n which can give you desired results, or identifying an h of n which can estimate what is happening to your signal, okay? And then effectively implement it. So this is these are again few examples of a system. An ideal delay is a linear time invariant system. This is averaging, that you go m samples ahead and n samples back, add all of them together. So wherever you are standing, I ask you add the next 2 sample and previous 3 samples. Then you move, add the next 2 sample, previous 3 samples. The system will still be linear and time invariant, right? You are using, but usually we don't have future samples. So in 1D signal processing, you avoid using the future samples. In image processing, you can use future samples because you acquire the entire image. So this, I have already concluded this expression, that is like, we know this is how you this is another way of just looking at it. This is a general signal, weighted shifted impulses, and you apply a transformation which is linear. A linear mean you need not to worry about addition, you need not to worry about scaling. So this is addition, this is scaling, so bring this operator directly here. And if it is time invariant, that a shifted impulse will bring a shifted impulse response. So this is the most important expression in signal processing. This is called convolution sum or convolution expression. So this expression is most important single expression which you keep hitting. So this is a mathematical expression. Interestingly, if you just replace n minus k by m, right? So replace n minus k by m, then k will be n minus m. So this x of k will be n minus m, or this will be h of m, and summation will now run over m. Now replace m by k, so this will give you k goes from minus infinity to plus infinity, h of k x of n minus k y of k y of n. So this is again two mathematically equivalent expression. Okay, mathematically both are equivalent expression. Usually we like this expression more, and I'll tell you why. This expression more, but these are two equivalent expression. By the definition of LTI system, we came up with this expression, which says really the output is weighted shifted impulse responses, right? Because now in signal processing, this we write as a convolution of two signals, x of n, h of n. Interestingly, h of n, we just saw h of n was a signal, x of n was also a signal. We did an example, I asked you if this is what the system is doing. Okay, so system h of n is this, and x of n is, let's say, this. So what is the output? What if I bring this on this side, this on the other side? What will happen? You'll get the same answer. Both are signals, right? Mathematically they are equivalent. Whether you convolve this with this or h of n with x of n, you are going to get the same answer. Okay. Mathematically both are equivalent. Mathematically this expression is equivalent to this expression. Why we like this expression more is, let's say this is the impulse response 0, 1 and 2. Let's say this is a constant value h0, this is a constant value h1, this is a constant value h2. Okay, this is my h of n is a constant value at 0, a constant value at h1, h2. So I say the length of the impulse response is equal to 3. There are 3 impulses in my impulse response. 3 impulses in the impulse response, so the length of the impulse response is equal to 3. So if I write this expression, if I open up this expression, now I know I only need to go from 0 to 2 because h of k is only going from 0 to 2. H of minus 1 is 0, so I need not to really expand this summation beyond 0 and 2. If I open this up, I get h of 0 x of n plus h of 1 x of n minus 1 plus h of 2 x of n minus 2. Okay, and this is the second interpretation which we started with. Take the current sample, multiply it with h0. The previous sample, xn minus 1 is the previous sample. If you are computing the nth sample, this is the current sample. The previous sample multiplied with h1 and previous to previous sample multiplied with h2. Right? So you can, in word, you can write it like this. A system, this is a linear time invariant system in which the current sample will be multiplied by h0, the previous sample will be multiplied by h1 and the previous to previous sample will be multiplied by h2. Means if I come here, I say current sample multiplied by this, previous sample multiplied by this, previous to previous sample multiplied by this, add them together, get one answer. Now move to the next index, repeat the same. Next index, repeat the same. So you'll get the both answer, the same answer. So one way of computing convolution is that for every impulse you make an impulse response. Right? For every impulse, make a impulse response, then add all the impulse responses together, you get an answer. That is not very trivial to code. This is very trivial to code, that you acquire the current sample multiplied with h0, you need to keep previous sample and previous to previous sample. Multiply the previous sample with this number and previous to previous sample with this number, then you update your sample, because now the current sample will become the previous sample will become the previous to previous sample. Okay, and just keep repeating this and you implement a system. So two ways of looking at a system, both are equivalent, analytically equivalent, but two different implementations. And you will keep learning about more and more implementations. There's number of ways of implementing a system. These are just two. One is saying copies the impulse responses, add them together. The other is saying no, just think of it as weights. The current sample with this weight, the previous sample with this weight, the previous to previous sample with this weight. Okay, the length of the impulse response will tell you that how many samples are you using to compute an output sample. So in this, how many samples are we using to compute an output? 3 samples. Okay, so this is the cost you pay. The cost of the system is 3 multiplications and 2 additions. To compute an output sample, you need to do 3 multiplications and 2 additions. If I say no, I really cannot design a system with 3 constant values. I really need to design something. You ask me to design something and I sit on MATLAB and come back and say, oh, this is really taking 216 samples. What is meant by 216? If an impulse response length is 216, what is meant by that? To compute an output sample, how many multiplications you need to do? 216. And how many additions you do? 214. So what is good, that a designer always tries to minimize. Once you are designing, you are only designing an edge. Right? So you try to minimize edge. You try to design, give the desired results, whatever that desired is. I'll show you in a while. And try to do that in minimum possible number of samples of your impulse response, because this directly dictates the complexity or the price of your system. Right? But these are the 2 ways. And so weighted shifted, if it is, so let me also highlight this. If it is 1D signal, all we say is, okay, you have the signal, and system means that you current sample multiply by something, previous by something, add them together, then come here, do the same, then come here, do the same. So it is really a mask. Let's say if this is the order of the impulse response, the current sample by 2, previous sample by 1, previous to previous by 3. So always do this. Next time, once you are computing output for this, you bring this mask here, right? Once you are computing for this, you bring this mask here. So usually once we code, we write this H in reverse order, because this is your h of 0, h of 1 and h of 2. The current sample you multiply by h of 0, the previous sample you multiply by h of 1, and the previous to previous you multiply by h of 2. So you write it in inverse of, so write h2, h1, h0, and then take this, add them together, move, multiply, add them together, move, multiply, add them together. And this is for 1D signal processing. And what if you are doing 2D signal processing? Same, the mask will be two-dimensional mask. Usually either it is 3 by 3 or 5 by 5. So if you are computing this sample, so you put this mask, so this pixel gets multiplied with this value, this with this value, this value, this value, this value, this value, this value, and then you add them together to get one pixel. Then move the mask, again do the same, again you get one pixel, then move it, again you get one pixel. I'll show you a pictorial view of this, but this is the convolution, and the signal processing revolves around convolution. Okay, and this is how we interpret this, that a signal is disintegrated into weighted shifted impulses. For every impulse, for delta of n, the output is an impulse response. Then for weighted impulse response, weighted shifted impulse, weighted shifted impulse response, weighted shifted impulse response, add them together. So if you add all the left side together, you get the input. If you get all the right hand side together, you get the output. So this is your answer. Okay, so an impulse response is this, and these are the two ways of implementing it: weighted shifted impulse responses, or always weighting the current sample and the previous sample and the previous sample and adding them together to get the output. Both are equivalent expressions. This is the image processing. In image processing, it's not 1D, it's a 2D mask. For example, here it is 1 by 9, 1 by 9, 1 by 9. So every pixel, basically you are adding all the pixels together and then dividing it by 9. It's averaging. Okay? So you do it like this. So once you are here, you start here, you have 9 pixels. Okay? So each pixel, basically you multiply by 1 by 9, add them together, and you compute only one answer, one pixel, and then so this is your answer. Right? Then you just keep doing this. So keep moving it, move the mask. So computationally intensive, because to compute one pixel you are doing 9 multiplications and 8 additions. Okay? So but you just keep doing this, and image will be filtered, or the image goes through your system to get the desired results. So what are those desired results? Why I take this example? Because it give you better visualization. So this is an example. An image, once you say you are taking samples in space, the sample value usually varies from 0 to 255, 8 pixels, 8-bit pixel. So you have nothing but a matrix. An image is nothing in signal processing but a matrix, a 2D matrix, and each value represents a grayscale, and that's what your monitor does, that it takes a value and assign a grayscale to that and paste it in that box. Right? So now I'm saying if I am here and computing this particular pixel, I add this plus, I add all of them together and divide it by 9. So what I get is 5.44, because I always deal with integers, so I throw away 0.44, so answer is 5. Okay? So I here instead of 6 I write 5 in the output. Okay, so image, and these are examples. This is the same filter applied on this image. It will blur the edges. Why do you want to blur the edges? Let's not at this point worry about it, but this operation will blur the edges. Okay, this is another, it's called Gaussian. So magic is figuring out these numbers. Remember, it's not very trivial to figure out these numbers. Okay, for a desired result you need to know these magical numbers. And how many? 3 by 3 or 5 by 5 or 7 by 7 or 9 by 9, you don't know. Okay, for in this example these are 5 by 5. Right? So you are computing this value, and for every pixel you need to do 25 multiplications and 24 additions. So you do this. So this is what it does. So Gaussian edges are sharper than the boxcar filter. This is the edge detector. I'll work like this. Again, these are the two matrices, and these are again other edge detectors. I'll give you edges. So again, if this is the desired results, we apply. One gives you the vertical edges, the other one gives you the horizontal edges. Okay, so this is another. This is so this is yet another edge enhancement where you apply this particular operator, then subtract it from the original image to enhance the edges. So this is what you are. So nowadays these are in your digital cameras. All these filtering and features are there in the camera, which does it in real time. So doing all the processing in real time. So you can sharpen the edges. This is low pass filter. This is the differentiator. Again, this is the mask. Okay, so this is the mask. 1 0 minus 1 2 0 minus 2 1 0 minus 1 will do this to your image. It'll just give you all the edges. So if this is desired, you apply this mask. And how you come up with this mask, not an easy science. It just requires some understanding, but especially, so these are the edges. This is removing, smoothing, removing the noise from the image. This is again extracting edges. So to conclude, we have seen two ways of performing convolution. So one is as a computational formula for computing y of n, y times n from the entire sequence x and h, and the other one is doing this, making copies of h of n and then adding them together. Yet there is another interpretation which we'll cover in the next class, but so this is the same mask. So you think of it as a mask and keep moving the mask. Okay, so start here, then bring it here, then bring it here, then bring it here, then bring it here. Just keep moving the mask and multiply these numbers together, add them, multiply these numbers together, add them. So the mask h of n is moving all the time. This is one interpretation. This is what the answer you get. So we'll come back, do this, but I briefly want to show you something which is very current. So the current is, usually there used to be a single input, single output systems, especially communication systems, that you have one transmitter and one receiver. Okay, this is called a single input, single output system. You only need to worry about one channel, h of n. Okay, one antenna, you need to worry about only one channel, h of n. Somehow if you can figure out h of n, then you can design an effective system, because you can take away the h of n. So you want to, then people started putting diversity. This is called space diversity, that you transmit using one antenna and you receive using two antennas. So there are now how many systems? Two systems, because this and this, right? A transmitter going to this and the transmitter receiving this. So both have different h of n. Why? Because they have two different systems. So they have in different physical environment. So this is where you need to deal with two, one h1 of n, another h2 of n. So need to deal with two. Then sometimes you transmit using two antennas and receive using one antenna. Same case. So you are transmitting using two antennas and receiving using one antenna. So you need to deal with two systems. You need to figure out two systems. Now the things are moving where you transmit. So all these modern communication equipment, Wi-Fi and other stuff. So the fourth generation is moving towards this, that you have n antennas. So you may, your even 802 dot something will have two antennas or four antennas. You will be transmitting using, your base station will be, your access point will be transmitting using multiple antennas. You will be receiving using multiple antennas. So what is there? So if you have 1 2 3 transmitter and 1 2 3 3 receiving antennas. Okay, so how many channels do you need to worry about? 9. Because this coming here is 1, and signal this antenna is transmitting is also coming here 1, and signal which this transmitter is transmitting is also coming to this antenna. So 3, for every antenna you have 3. Similarly, this is totally a different channel because they are physically placed at different location. So you should need to deal with 9, a matrix and each of this path has multiple paths. So it has an impulse response. Let's say 2, 3 and 5, and it will have -1 and 5 and 2 and 0, 1 and 5. So very interesting and current area of research to estimate not a channel but a matrix of channel. It's a matrix. We say it's a matrix. It will have 9 entries, and every entry is a channel. Within every entry, if there are 3 paths, you need to figure out 3 coefficients. If there are 5 paths, you need to figure out 5 coefficients. Okay? So this is where the technology is moving, and these are called MIMO, multi-input, multi-output system. They are of special interest to us. Why? Because each antenna transmits a different stream of data. So the same data is coming. You are not transmitting same data using all the transmitter. So each transmitter is transmitting different data. So what you receive here is not a clean data which is transmitted by this signal, this transmitter. What you receive at the receiver is the data being transmitted from different data from different transmitter, gets through your channel and hit the receiver. So this is the MIMO channel, and this is a system, a complex system, where a system of systems, or you can call it like this. It's a system of systems. So you have 9 of these. And estimating this is, you can find PhD thesis on these. So how to estimate this is one problem. And once you have estimated, then how to counter this? Because you got to counter it to extract the signal. Right? So, but this is very attractive for engineers. And why it is very attractive solution? The reason is that if one transmitter can, let's say, transmit 1 megabit per second, and you have 10, so you can effectively increase. It's all about data rate. So you want more and more data rate. This edge technology and GSM technology and 4G technology, it's all about that you want to put more and more data in the same channel. So this is how it is being done, that you, in the same system, a same mobile phone will be having multiple antennas, receiving antennas, and the base station will have multiple transmitters. So every transmitter is throwing different bits, and you got to then recover that. So this is the FIFO MIMO systems. I just wanted to point this out, and once you will be doing your projects, as you can take these topics, I'll keep showing you topics, just think what excites you, start just learning about it. So these are the MIMO systems. A channel estimation is a problem, which is finding capital H, and then designing a reverse of H is also a problem. Okay, so next time once we come, we'll